All right. So today we're gonna start lecture 2. And the topic of this lecture is going to be from quantum particles to quantum fields. So this is to be compared with lecture 1 that I'm going to summarize now. So in lecture 1, what we discussed was going from classical particles to classical fields. We started with the whole discussion was classical physics. So we started with the discussion of classical single particle in D that moves in D spatial dimensions. And Hamiltonian language or Lagrangian language, we are dealing with a bunch of generalized coordinates. In the Hamiltonian language, we have their canonical conjugate momenta, PIs. But in the Lagrangian language, you're dealing with QI and QI dots. And I runs from 1 to D, representing the generalized coordinates. This is a single particle, single classical particle in D-dimensional flat space, RD. Classical fields in 0 plus 1 dimension, classical fields are a set of functions, phi's, that are functions of space-time. We take them to be smooth because we're going to be taking derivatives of them. And then there is a Hamiltonian, meaning that there are canonical conjugate variables, pi's, that are also functions of space-time. Or you could formulate things in terms of Lagrangian formulation, talking about phi dot, and spatial derivatives of phi, because the field has that dependence. Now, if you take classical fields in 0 plus 1 dimensions, it means that there are no xi's. And if you have D copies of the field, you can see that by change of variables phi I going to qi, what you obtained is you obtain that classical field, D classical fields in 0 plus 1 dimensions, just in time, is equivalent to a single particle, classical particle moving in RD. Any questions about this? We said that field theory is an intrinsically multi-particle theory. We give an example of multiple particles. This is the XY model. We wrote down a local nearest neighbor Lagrangian XY model, right? These are rotors. They are Heisenberg. There are two-dimensional spin degrees of freedom, and this is a coupling, one-dimensional chain of rotors. We saw that the vacuum wants all of them aligned, so the vacuum is twofold degenerate, and the low energy states have long-range correlations that if the correlation length is much larger than the lattice sites, then you could squint a little bit and see these fluctuations, long-range fluctuations, as continuous fields, right? This is the so-called continuum limit, when the correlation length is much larger than the scale of the lattice. The number of particles within one correlation length goes to infinity. This is a limit that field theories emerge, so-called statistical field theory. So if I want to summarize it, many particle systems near criticality on a D-dimensional system lattice. Criticality is a statement that the correlation length is very, very large. That happens in critical systems near the so-called continuous phase transitions. This is just in case you want to go and read about them. But this is the same as the statistical field theory in D plus 1 dimensional space-time. We said that these in low energies, collective excitations can emerge that are different, that could be different from the high energy particles, degrees of freedom. These we call the quasi-particles. They can have different properties. Sometimes they have this different statistics. We gave an example where their particle number is not conserved. They could be pair created or annihilated. And field theory naturally captures that, and that is what is meant by saying that field theory is an intrinsically many-body system model. Questions? So this question is somewhat high level. This was all classical physics. right? Today, what we're gonna do is we're gonna run this analogy in quantum mechanics, right? All right. So what is a single particle quantum mechanical system? Where if you have a single particle, quantum particle that moves in d-dimensional flat space, what you have is you have the same qi's and pi's, the generalized coordinates and their conjugate momenta, but now they're operators that depend on time, right? And the Hamiltonian, which is an operator, it's a function of q hat and pi hat, right? It's a positive function, positive operator, decides their evolution through the Heisenberg equation, right? So that's a single quantum particle moving in d-dimensional space-time I. The index I runs from 1 to d. This is just good old quantum mechanics. Now, what are quantum fields in RD? Quantum fields are a set of phi hats. These are fields of variables x, I, and t, right? And their canonical conjugates pi hat of x, I, and t, and the Hamiltonian is a function of these. So one thing that you immediately see is the following. In quantum mechanics, time and space are treated differently. Time is an external parameter, it's absolute, whereas space we promote to operators. So we treat time and space on completely different footing. In field theory, we treat them the same, on the same footing, because it's sort of required, because we're going to be talking about relativistic theories. Relativity, one of the lessons that we get out of relativity is that space and time should be treated as a part of a package. There's this flat space, RD, 1, right? So they should be treated the same. So instead, in quantum field theory, instead of promoting time to an operator, what we do is we make space a parameter and a field, we define a field that depends on these parameters, right? So let me repeat that. In quantum mechanics, quantum field theory, because we're after relativistic theory, we have to treat space and time on the same footing. And we achieve that not by promoting the time to an operator, but by making space an absolute variable. Nonetheless, we have fields, these external these functions that are operators of space and time. They come with their canonical conjugate momenta and a Hamiltonian. Now it's pretty clear that if I have d copies of the fields in 0+1 dimensions, by the same analogy that we went through, d quantum fields in 0+1 dimensions is nothing but quantum mechanics of a single particle in RT. Any questions? So this is just the same analogy applied in the quantum mechanics. Questions? All right. Where do quantum field theories come from? In classical physics, we argued that classical field theories come from low energy limit of these many particle systems where low energy excitations have these long range correlations, these long range waves that include many lattice sites. So they basically look, for all practical purposes, they look like continuous functions. Here, the principle is very similar. If you are, and also in classical physics, we saw that at fine temperature, thermal fluctuations could lead to pair creation. So if you have a system in finite temperature, right, the system has fluctuations. We said that there is a phenomenon of pair creation, but you need energy to pair create. That is provided to you by the thermal fluctuations, the fact that the system of finite energy at finite temperature has its energy can fluctuate. It can swap energy, interchange energy with the bath, right? In quantum field theory, what happens is that if you have a continuous phase transition, a system such that the correlation length is much, much larger than the lattice size, we obtain a multi-particle quantum system that is a quantum field theory. These smooth fluctuations we're talking about are present. They're described by quantum field theory. However, as opposed to this case, where we had to be at finite temperature so that we have thermal fluctuations to create particles, to pair create, here, even at zero temperature, due to quantum fluctuations, we could have pair creations. So this is a very high level idea of what distinguishes statistical field theory, which is purely classical, from quantum field theory. Here, a thermal two-point function captures fluctuations, linear response. Here, vacuum two-point functions capture fluctuations. All right? We're setting the stage for a course, so I think a lot of this will make sense halfway through the course, or perhaps even by the end of the semester. All right, any questions? All right. Now, here I want to make something very clear. As opposed to the field theory in classical, statistical field theory in classical physics, where it was just relevant for some limits of low energy limits of certain systems, here in quantum mechanics, we absolutely need quantum field theory simply because of the relativity. The statement is that relativistic quantum mechanics is inconsistent. As simple as that. What I just said doesn't have an analog in the classical story, right? So I motivated the classical field theory from as a multi-particle theory, blah, blah, blah. But there was never a sharp problem that forced me to use the field language. There were alternatives. I could have used particle picture if I was just like, it's a pain because you have to take the particle number to be not conserved. But here, importantly, relativity leaves you no choice. So I'm going to mention a couple of problems. Today's lecture is all about that. A couple of problems with relativistic quantum mechanics that force us to use field theory, and I'll comment on how field theory fixes these problems very briefly. Probably the comments are somewhat cryptic because I haven't taught quantum field theory to you guys. They will start making more sense as we get deeper into the course, right? Is the principle clear? So this is the bulk of this lecture. I'm gonna summarize how quantum mechanics and relativity are inconsistent without QFT, without quantum field theory. You simply cannot have quantum particles. Single quantum particle that's relativistic is not a sensible theory. All right, good. Questions? I'm gonna list 3-4 problems. I don't recall how many. We're gonna go through them. All right. First thing, in a relativistic theory, particle number cannot be conserved. In the classical case, I gave an example where it was the case. You might say, oh, it was specific. Maybe it's specific to that example. Maybe it doesn't always work. Maybe it's, like it's not a must. Here, I'm going to run an argument that tells you because of relativity, in quantum field theory, there cannot be conservation of particle numbers. There simply cannot be. So Heisenberg. So here's the Heisenberg uncertainty principle tells you that del P, del X is larger than H bar. Good. Now imagine you're dealing with a photon. For a photon, delta E is delta P times C. C is speed of light, right? That means that delta E is larger or equal to H bar C over delta X. There is an uncertainty in energy which is related to delta x. So now, here's what happens. If you try to localize a particle at very, very small scales, right? That's delta x. This site becomes large, which means that your certainty in energy grows, uncertainty in energy grows. If you try to localize a particle in very small scales, that can lead to large energy fluctuations and cost. And then from relativity, you know that delta E is 2mc squared. If the particles have mass m, and you have a particle and antiparticle, create, like electron, positron, the energy cost of this is 2mc squared. You put this on this side, you learn that there is a delta x, that if you try to localize a particle at scale smaller than delta x, energy uncertainty is enough to create particles out of vacuum. So it's simply not possible to do that. Good. One way of saying it is that here's an atom, right? You want to localize it at very small scale. So you try to observe it, right, with a photon that tells you where it is. Of course, from basic optics, you know that to see a particle or localize a particle at very small scale, you have to use very high frequencies. Those high frequencies will mean large energies. And once the energy is enough for creation of a pair of particles, electron, positron, for example, you will pair create. So this simple argument, uncertainty relation and relativity, basically tell you that there is just no way in quantum field theory that you could have particle number conservation. So here's a quote from one of the founders of quantum field theory. There are no real one-particle systems in nature, not even few particle systems. Because once you can create a pair, this rule says, like if you try to localize even more and more, the energy gets larger and larger, you could pair create more. So the system must include all particles at the same time. It should be a theory of infinite number of particles, potentially many particle theory that includes everything. There's no way of consistently thinking of relativistic quantum mechanics with a fixed number of particles. Such a thing doesn't exist. This is argument number one. Any questions?
So where does the energy come from? Is that a stupid question?
Where does delta P, when you say delta X times delta P larger than H bar, where does delta P come from?
It comes from how precise you're measuring the particle, I guess.
It comes from the fact that in quantum mechanics, the particle simply does not have a fixed position and momentum at the same time. These are incompatible observables. The particle simply does not have a fixed momentum if it has a fixed x. There is no physical meaning to saying that the particle is at this point and has this much momentum. Once you say the particle at this point, then the value of P must be vague, right? It must be, there's a finite resolution to nature. Same is true here. There is no meaningful statement. So when you say where the energy comes from, it assumes that there is a certain amount of energy that the particle had, and that the particle that sits at a particular point in space-time had a fixed value of energy. Now you have a delta E to explain. That's not how quantum mechanics works. It says that if the particle is sitting at this point, there's simply no meaning to its energy up to such fluctuations, right? That's why we call them quantum fluctuations. Good?
I think so.
Any other questions?
Another question. So
Yes.
why the fluctuation of energy doesn't mean the fluctuation of angular momentum, but means the fluctuation of particle number?
So, well, angular momentum, you could, for the
Oh,
argument,
sorry, like angular frequency, like the omega. Like
for the argument I'm running, I don't need to talk about angular frequency. If you have a setup where there is rotation, that would also be relevant. The argument I'm running is that once delta E is equal to 2mc squared, right? There could be perturbation. There are amplitudes, right? There are transition amplitudes that allow for such processes. Did I address the question?
Yeah, but like the nodes afterwards say like there probably will be more particles rather than just pair creation. That's what you're trying to say.
Sure, but that makes my point even stronger. All I'm trying to say is that the number of particles simply cannot be constant. That's all I'm trying to say, right? A relativistic single particle does not make sense. That's an argument I'm trying to run. And to make that point, I'm just running it this way. But of course, you're absolutely right. You could create more particles. You could create particles with angular momentum if they have opposite angular momentum. So sure, that's allowed.
Yeah, probably my question is like, for example, if a photon, then the energy is just h bar omega. But if the energy has some fluctuation, why not omega can be fluctuating? But I need more number to fix the fluctuation.
So you see, the word fluctuation comes from what? It comes from, think of delta x, delta p. Quantum mechanics doesn't tell you that both of them have to be non-zero. Quantum mechanics gives you a choice. Make your choice. You want delta x to be small, make it arbitrarily small. But then you're not allowed to have delta p at the same time small. You cannot have them simultaneously small. It's perfectly fine to say I have a photon of frequency this much, and I know that very, very, very well. That's perfectly fine. That means that you have measured delta E, energy of that photon, really, really well. But that means that you've lost your delta T. That's the energy time uncertainty relation, right?
Okay.
It's a good setup to think about. I'm actually gonna say how quantum field theory fixes this. And then I'm gonna run a bunch of more of such problems. So quantum field theory solves the problem because it's an intrinsically many particle system. It's all particles at once. So you have the Hilbert space of a single particle, call that H1. There's a Hilbert space of two particles. If this theory is these are bosons, you know how to construct that Hilbert space, you tensor product them and symmetrize them, identical particles, right? Hopefully you've learned that in quantum mechanics. If they're fermion, you anti-symmetrize them. Then you could have a sector, a Hilbert space for 3 particles, 4 particles, 5 particles, and so on and so forth. So what is the Hilbert space of quantum field theory? You just take all these Hilbert spaces and direct sum them from H0, the vacuum with no particles, to H1, H2, H3, all the way to H infinity. We call that a Fock space. It's all particles at once, right? So we're direct summing. Does everyone know what direct sum means? So it's like putting block diagonal matrices. There are processes that change particle number in quantum field theory. And that's perfectly fine because this Hilbert space is large enough. It includes all the particles, and it will do the job. So second part of this course, we'll start with second quantization. Second quantization is we're going to spend a lot of time talking about this Fock space. We're going to talk a lot about this. But I'm setting the stage. It's a must. It's not a choice. It's not like because somebody Dirac said, oh, let's do this, we're doing that. It's a must. It's not, you don't have a choice. If you believe in relativity, that we better do, because we tested every day billions of times. And if you believe in quantum mechanics, that you better do, because you tested every day millions of times. The fact that the bulb lamp works is quantum mechanics. There's no way around ultraviolet UV catastrophe. All right. So that is problem number one. I want to repeat again. No, actually, I'm going to skip this. All right, problem number two. This is even more severe. No, it's not more severe. It's as severe, because each of these problems kill the theory of relativistic single particle or fixed number of particles. But anyway, relativistic quantum particles violate causality. So that is pretty darn bad, right? You simply cannot be causal. What does causality mean? Does anyone know? Can anyone give me a definition of causality?
Causes must precede effects in all frames.
Correct. So in quantum mechanics, it will be what? It would be that if you have an observable at time t equals 0, you have an observable at time t and distance x away. If x is larger than ct, these two observables must commute. That's what it means. Commute means what? In quantum mechanics, commute means that you cannot send a signal. It's no signaling. Hopefully, do you know why? Okay, I'm not going to push this anymore. All right. So let's calculate. Let's take a single particle that's quantum mechanical and try to see what is the amplitude for this particle to, after a short amount of time, to be arbitrarily far away. Quantum mechanics, if you recall, from, for example, path integral formulation of it, there's an amplitude for the particle sitting at point x to be at some point x prime at some later time, right? How do you calculate that amplitude? Here's x naught vector. So the particle is initially at ket x naught. That's deterministic, infinite Dirac delta function valued, right? Then I'm going to apply time evolution. It's a free particle. For a non-relativistic thing, here I have to put the Hamiltonian. For a non-relativistic thing, I would just put p squared over 2m, right? For a relativistic particle, I have to put square root p squared plus m squared, right? That's the energy. That's the Hamiltonian. That's the Hamiltonian energy of a relativistic particle. And then I look at this amplitude where x is really, really far from x naught, and t is not long enough so that the signal can propagate. This is called a free propagator in 3+1 dimensions. All right, so I'm going to do this calculation. It's, again, the calculation is going to be giving me what's the amplitude probability for the particle that I just measured is sitting at a point for it to appear in the Andromeda galaxy fraction of a second after. And the particle is moving freely, right? It's just like, the only thing that I know is that here's your Hamiltonian, relativistic Hamiltonian. I will review relativity. If you guys are unfamiliar with this, why energy of a massive particle with momentum free particle is this, I will review that, but I think you should probably read up on relativity, refresh your memory on relativity. All right, so here's what I have to calculate. What am I going to do? I'm going to insert a resolution of identity, right? Which is ket p bra p, integrate over all d3p's, three-dimensional particles moving in R3, 1. And here's the normalization. That's my choice of Fourier transform. All right, so now this is an eigen state of this, e to the power of minus I squared root p squared plus m squared comes out. This is just e to the power of ip minus x naught. I get x and p. From that, I get e to the power I p dot x. The whole thing is repackaged in this way. Are you with me? So far, it's all good. All right. So now,
sorry,
yes.
I had a question. What's the P density matrix for?
So
how
there's no density matrix. There's no
in the
density
second.
matrix. That's just resolution of identity for momentum eigenstates.
Oh, sorry. Thank you.
Right? Any other questions? All right. So this is the right. This is just resolution of identity. I'm just integrating over kit p broad p. That's just resolution of identity. Now, this you could integrate, and there's an. What have I done in the first step? I've used polar coordinates for p. So I've written this d3 of p as p squared dp because the only p dependence I have here is p squared. And here I can write this p, absolute value of p cosine of theta, which is some angle here. So these are typical field theory calculation integrals. I will ask you to do that in a homework problem as the very first problem. You do this integral, you do the, so it's a three-dimensional integral. You're going to do it in polar coordinates. You first do the angular integrals. This is what you get. Then you have to do an integral over p, the norm of the vector, the length of the vector, right? And you integrate this using Bessel functions. We don't need to do that. I'm just going to give you the answer, and I'll make you do this integral in your homework, right? So it's just an integral, but it's an integral that will appear a million times in quantum field theory. So it's important that you do it. The answer to the integral is this. So here's x minus x naught. That's the variable. I'm going to assume x naught is 0, right? So then this is just the length, the distance that I'm talking about, right? So this is just a distance. When the distance squared is much larger than t squared, I'm outside of the light cone. So if the probability, which is this amplitude squared, is not 0, I'm in trouble. Causality is in trouble, right? Because there is a non-zero probability for the quantum particle to just disappear from here and appear in the Andromeda galaxy arbitrarily far away in a fraction of a second, right? Okay, so you do the integral in your homework, you find that there is such an, that it becomes e to the power of m square root k x squared minus t squared. So basically, there's a non-zero probability. It's exponentially small in distance. So the distance to Andromeda galaxy is ginormous. So this is an exponentially small value in that ginormous. You have to take the exponent of it. It's teeny tiny. However, it's still a violation of causality. Causality is not an approximate law of nature. Einstein was not more or less right. He was not morally right. He was just correct, right? So this is nonsense. This is inconsistent. The theory is acausal. If you allow a tiny violation of causality, you could cook up crazy paradoxes, right? So there is a probability for the particle to leak out the light cone. As a matter of fact, this paradox is actually super severe. This problem is super severe. It has some origins in like deeper results in quantum mechanics, but we're not going to go there because I'm not talking about other approaches to quantum field theory. In some other approaches to quantum field theory, this story takes a center stage, but here we're just going to talk about it a little bit. All right, any questions about this? Is it clear what I'm doing? I just calculated the transition amplitude or the probability for a free particle that has relativistic dispersion to just travel superluminally. And that probability came out to be non-zero. So that's bad. Is it clear? So relativistic single particle quantum mechanics is nonsense. I cannot say this stronger. All right. Quantum field theory is gonna fix this. Does anyone know how? Any thoughts? Any wild thoughts?
The propagator itself is a particle, kind of.
Say it again.
The propagator itself is a particle, kind of.
No, that's not how I saw it. It's in a very bizarre way. Yes.
Is it the fact that you've now demoted a position from an operator to being a function of the field?
So that I have done, but there has to still exist a formulation in quantum field theory that describes the same phenomenon, right? In quantum
Mhm.
field theory, I have to be able to still talk about the propagation of a single particle. So you're absolutely right. I have gotten rid of the notion of particle, but in section 5 of the course, halfway through the course, I'll teach you guys how the notion of particle is introduced back in quantum field theory. Not as an absolute notion, but something that has to emerge out of it, like quasi-particle, right? It's some emergent concept. So we'll get there. But no, the solution is something else. The solution is this. You might have heard that in quantum field theory, people talk about antiparticles. Quantum field theory says every particle in nature has an antiparticle. Now, what is brilliant is that in the case that we're discussing, if you try to set up the problem, you find that the transition amplitude that describes the propagation of a particle from this point, x, to some point really, really far away, this amplitude cannot be distinguished. This phenomenon is indistinguishable from the propagation of an antiparticle in the opposite direction. Because every particle has an antiparticle, you cannot have one amplitude and not the other one. And they exactly cancel on the nose. They cancel out, and the answer comes out as 0. They cancel out outside of the light cone. However, once you're inside the light cone, they don't cancel out. We will actually explicitly do that calculation in a couple of lectures. But in anticipation for it, so quantum field theory, you might have heard about antiparticles. Antiparticles is not just something that just comes up and, oh, it's just something that comes up. It must be there. Quantum field theory explains it. It requires it, and it must be there to save relative causality. Causality cannot be saved otherwise. Good? We're going to go through these gradually. So instead of, I'm just priming you guys for the calculations that are going to come later, right? But telling you that there are these essential things, this calculation that we're going to come, that you're going to be doing a lot of ugly integrals. Those ugly integrals you're going to be doing, they're for a reason. Just to save, it's a very valuable, there's a important thing at stake, saving causality. All right, any questions? Now, the third problem, which at this point might not seem like too much of a problem to you guys because you're still learning the basic formulation of perturbative quantum field theory, but this is a severe problem at some fundamental level, is the problem of so-called strong coupling, the so-called problem of strong coupling. So in quantum mechanics, how do we describe a single particle? We describe it as a wave function. And if it's localized in space, the wave function has a peak somewhere and there's some sort of width that decides a delta x, right? Now, what is the meaning of two particles in quantum mechanics? It's really two wave functions far away, right? It's like an excitation like this. Now, you've learned that fundamental particles, and if you see a wave like this, you could tell, with eye, you could tell, oh, this looks like two individual particles, right? Because they're really far apart. Now, you've learned that in quantum mechanics, we're dealing with indistinguishable particles. So there's no way of saying that, oh, this is blue, this is red. right? All you see is like a wave function that looks like this, which tells you that if you bring these two particles closer and closer, or if the interactions is very, sorry, no, one thing. Actually, from here I should conclude a little bit differently. The notion of a particle, number of particles, is an asymptotic notion. It's a notion that's sensible as you separate them really, really far apart. Otherwise, the waves are going to be all, when you have a bunch of particles that are indistinguishable and near each other, you look at the mess of a wave function, you cannot tell how many peaks there are and how many particles there are. It's only a meaningful statement as you pull these guys apart to infinity. Good? Is that good? Why is that relevant? Because as you pull these guys apart, the potential goes to 0. So the wave functions just add. So you have a bump here, you have a bump there, right? You're solving the Schrodinger equation without the potential. If you take two solutions, you add them up, it's another solution, right? Now the problem comes up when, as you separate the particles, the potential doesn't die away. The potential is very strong. This is the problem of strong, I explain this. This is the problem of strong coupling. For example, imagine two fundamental particles, they're called quarks. We're gonna discuss this in detail in this course, quark and antiquark. As opposed to two electrons or like other particles that as you separate them, the potential between them drops. These are the opposite. As you try to separate them, the potential between them grows. So basically, you're never ever gonna be finding individual quarks in nature. That costs insane amount of energy. You're never gonna find them. So if you never find them, that particle is not in the description of your theory. So what is in the description of your theory? You look around, all you see is you never see individual quarks, you see bound states of them. In mesons, these particles that have a pair of Q and Q bar, quark, antiquark, packaged together into one individual package that moves together. They always move together. This is called a meson. This is a quasi-particle. Or another quasi-particle that's perhaps more famous to you guys, more familiar to you guys, called proton. Right? So from the point of view of quantum chromodynamics, the theory of strong forces, quark is a fundamental degree of freedom, fundamental particle. However, we never see quarks. In the universe around us, we only see protons. Protons are emergent quasi-particles at low energies. And it has to do with the fact that there is no way on Earth we could isolate the quark from a proton. Never, we cannot just pull out a proton. Yes, a quark out of it. Yes, we can, but it takes billions of dollars of electricity bill in LHC that we're not willing to pay in the environment around us. And that's good because it's dangerous, right? So it just takes an enormous amount of energy. Around us, we don't have that. We never see that. What we see is proton. Proton is a quasi-particle. Meson is a quasi-particle. These are low energy emergent degrees of freedom, right? So this is the quantum analog of those up-down quasi-particles that were moving along. And I said, oh, this looks like, from the point of view of somebody in low energy, this looks like a quasi-particle. It's similar. So at strong coupling, the whole notion of what is a particle, fundamental particle, how many of do you have, or because there's no, you simple, as I said, this particle number is as an asymptotic notion. The reason that proton exists is that once that you package these guys as up, down, down, up, quark, down quark, now these groups of 3 of them, they interact weakly. And as you separate them, you could pull them to infinity with a reasonable amount of energy. And I would say, oh, I have one wave function that's localized here, one wave function that's localized here. There are 2 protons. Yes. Now, this was a coincidence. There are theories in nature that do not admit quasi-particle pictures. As in, the interactions are so strong, and they just happen to be such that there is never any notion of a particle. What they are, they're just a mess of a quantum soup. There is no particle. They're just like insane quantum fluctuations. There's no excitation that can just move around freely. There's no such a thing. These are quantum soups. Good luck. There's no particle. Where are you even going to start with quantum mechanics, particle mechanics? It doesn't exist, right? Quantum field theory turns out to be the right language to describe this. It won't be in terms of the Fock space, but we will introduce the path integral formulation of quantum field theory, and that's our approach. This is really crucial for understanding the universe around us. All right, is this principle clear? The only way to describe this quantum soup is using quantum field theory, not particles. Quantum particles will not get us anywhere.
Does this actually exist? Like quantum soup?
Yeah, of course. We
So, like,
produce
are
this in
there-
Greg.
Like
Yes.
what are examples of quantum soup?
Quark gluon plasma. Quantum soup is a made-up word, right?
Mhm.
I'm trying to give you an analogy. Quark gluon plasma that we produce in REC. REC is a laboratory where we collide really heavy protons, but not like LHC. It's in different phase point in the phase diagram. You produce this quantum mess. It's this like bizarre. It's called quantum quark gluon plasma. It's a plasma. There's no clear particles in there. It's actually not properly understood because it's deep in the strongly coupled regime. But generically, it's true. As a matter of fact, there's a large class of quantum field theories that are relevant, that admit absolutely no particle description. Some of them, they describe really mundane looking physics near you. For example, I described to you guys that at finite temperature, there are phase transitions. There is a phase transition at the tri-critical point of water. Water, in the phase diagram of water, there's ice, there's gas, there's liquid. There is a point that's called tri-critical, which is like these phases meet. In the vicinity of that, you have a continuous phase transition. There's a field theory that describes that continuous phase transition. It's a conformal field theory that has absolutely no particles. It's a very well studied theory. Well, it's a very important theory. Conformal field theories don't have notion of particles. And those are actually some of the well understood models. Yeah. Any other questions? We will not get to
Yes,
that.
Naima, I have one question.
Yeah.
Yeah, like earlier when we defined the Hilbert space for QFT, we said it was the Fock space. That is, it was the summation of the individual Hilbert spaces of the particles. So
Yeah.
now, if we do not have any notion of particles, like, so how
Correct.
do you still define the Fock space? Because N is not very
I do
clearly
not.
defined.
I cannot. I
Okay.
cannot. The Fock space picture relied on the existence of some quasi-particles. So we'll see that in this course, we're going to start with perturbative quantum field theory. That's where the Fock space is well defined. We'll make sense of that. However, once we go in the deep and then we introduce path integrals as an alternative equivalent method. It turns out as we go deep into the strong coupling regime, the Fock space pictures is no longer useful because we simply don't have particles. However, the path integrals are really our only guide into that dark world of strong coupling. That's the only way to model them.
Okay, but can in this case we can make any comment about the Hilbert space now? Like, how do you define the Hilbert space now?
Path integrals.
Oh.
There's
Okay.
a formula. There's a reformulation of quantum field theory in the language of path integrals. Okay. We'll get there. We'll get there. All right. Any other questions? By the way, how am I doing on time? We started when? 11. Okay, 50 minutes in. Okay, good. Any questions? So to summarize this point that was just made right now, in this course, we'll discuss quantum field theory from 2 points of view. the so-called second quantization. This is a particle, fundamentally a particle-like approach to perturbative quantum field theory. Perturbative means where in the regime where interactions are small, the notion of particle is well defined. However, it's not conserved, right? So you do that thing that I was saying, all particles at the same time. You do this sum over arbitrary Hilbert space of arbitrary number of particles to construct a Fock space. That goes with the name of second quantization. Second quantization is an important conceptual framework to understand quantum field theory in the weak coupling regime where interactions are small. We also introduced a second approach, Feynman path integrals. The second quantization is intrinsically Hamiltonian based, whereas the path integral quantization is Lagrangian based. They're related. It's unfair to call path integral quantization Lagrangian based, but usually the usual formulation is like that, because we'll see that there will be path integrals in the phase space as well. However, the interesting thing is that the path integral formulation could formally be extended deep into the strong coupling regime, whereas the second quantization picture falls apart. If you hear people talk a lot about path integrals in quantum field theory, and not as much as in quantum mechanics, there is in quantum field theory, there's a dark strong coupling regime where you have access to it only through path integrals. Whereas in quantum mechanics, you can always do standard quantum stuff, operators and stuff. Good. It also turns out, you'll see, it also turns out the path integral quantization is a lot more simplifies calculations a lot. It's a lot more elegant in some situations. All right, it's a natural point to stop and ask for questions. So summarizing, we went over how many? Three problems with that said quantum field theory is not just a choice. It's a must. Once you have relativity, strong coupling, quantum mechanics. It's a must. You have to use it. And these arguments, the problems that I mentioned, we're going to go through them. They're going to come up in our calculations again. I'm just presenting them in anticipation for the calculations that you're going to see and do. Questions? All right. So I talked about the things that quantum field theory necessitate quantum field theory require quantum field theory. But now there are also a bunch of things that are advantages of quantum field theory. We didn't really have to have them, but they actually nicely come. For example, quantum field theory explains things we see in nature that we had to put in by hand in quantum mechanics. For example, the antiparticles. Now, I just told you that quantum field theory solves causality problem by introducing antiparticles, right? But at some deeper level, you're going to see that antiparticles in quantum field theory is not a choice. It has to be there. It's not a choice. It must be there. Once we get to representation theory of quantum particle group, it must be there. And we see antiparticles around us. That's good. In quantum mechanics, we just had to say, oh, you know, in quantum mechanics, you could have solved the problem of causality by saying just there's a principle of nature that every particle comes with an antiparticle. You could have solved the causality problem in quantum mechanics by saying those words. But those words you would have just had to take as a principle of nature. Here in quantum field theory, you don't have to take it as a principle of nature. It simply comes out of relativity. It must be. Is that clear? So what is an antiparticle? If you have a particle of mass m and charge q, an antiparticle is a particle with the exact same mass and charge negative of that. So what I just said is a little bit oversimplified, but we'll get there. We're going to discuss that. For example, every fundamental particle in nature has an antiparticle. Electron has a positron. Positron has the same mass, but opposite charge as the electric charge, it had positive charge. Proton and antiproton. Now, proton, you realize that is not a fundamental particle, but anyway, it's longer story. Now, there are some particles that are their own antiparticles. Example, pi naught, z naught, photon, graviton. Good. So the necessity for antiparticles, in particular antifermions, was observed within the theory of quantum mechanics back in the days, in the 1920s, pre-quantum field theory. So fermions, for example. So Dirac at the time invented this theory that I think they still teach in condensed matter. It's called the particle hole theory, to explain antiparticles for fermions, because it was a fact. We see fermions come with antiparticles, and Dirac had to explain that. So he came up with this theory called particle hole theory. There are these Fermi surfaces, blah, blah, blah. So if you believe Dirac, you come up with particle hole theory, and you can say, oh, I've explained antiparticles in quantum mechanics. There's a problem with that. This particle hole theory might explain the antiparticles for fermions. However, there exists no such an analogous theory that would explain the antiparticle for bosons. It just doesn't exist. So quantum field theory is inevitable. If there is one message I want to send across today, is that quantum field theory is inevitable if you want relativity and quantum mechanics.
Sorry,
Yes.
I have a question. When I have an antiparticle, I revert the electric charge or all the other charges, like hypercharge or so.
We'll get there. That's why I said this is oversimplified.
Okay.
We'll get there. Yeah, here I was just talking about electromagnetism, therefore charge is minus that. Does anyone know the answer to that question actually right away? Well, okay, never mind. Yeah, it will be a big part of the course. All right. All electrons are identical. Quantum mechanics says that identical particles satisfy different statistics. It could be bosonic, fermionic, or they could have parastatistics. What is a boson in quantum mechanics? It's something that has its wave functions, multi-particle wave functions, has to be symmetrized, right? That's the definition of boson in quantum mechanics. This is one of the issues that I have sometimes with students. You ask them, what is a fermion in quantum mechanics? And they tell you that it's a spin half particle, blah, blah, blah. Not according to quantum mechanics. According to quantum mechanics, a fermion is a particle that has the following property. It has fermionic statistics. Its wave function has to be anti-symmetrized. From the point of view of quantum mechanics, every particle has a spin, and it just happens to be the case that fermions have half integer spins and bosons have integer spins. This is just an observation in quantum mechanics. Quantum mechanics has no way of explaining this. Quantum field theory has a theorem, a crucial theorem called spin statistics theorem, that says integer spin must have bosons. Why? Because of causality. And half integer spins must be fermions, integer spins must be bosons, half integer spins must be fermions to save causality. Otherwise, causality is in danger. We're going to actually go through an example of this proof, a mini version of the spin statistics proof, right? So let me repeat this. In quantum mechanics, not relativistic quantum mechanics, spin is a property of particles. Statistics is another property of identical particles. And they're not a priori, according to some principle of quantum mechanics related. It's relativity that says integer spin must be bosonic, half integer stream must be fermionic, and it just happens to be what we see in nature. From the point of view of quantum mechanics, it's just a coincidence, just something that we see. Is that clear? So in this course, at some point, we're gonna prove a spin statistics theorem and a small version of it. Good. So it's a very crucial thing. Spin statistics in quantum field theory was perhaps one of the huge successes. It's early days of quantum field theory. Sorry, it's like we're talking about the really early days of quantum field theory, but it was crucial because it explained something we didn't know how to explain. And the principle at work here is causality, like a lot of other things. Where when relativistic quantum mechanics fails, it cannot explain something. It's just because causality is not respected. Any questions? So, actually, let me see. All right, any questions? This is a good moment to pause because I'm gonna switch gears a little bit. So what have I done? Let me summarize. Lecture 1, we went through this argument and discussions of how in classical physics we are dealing with particles. And then if you have multi-particle systems near continuous phase transition, there are these long wavelength things that look like fields. And then in the low energy, you might end up with a theory that's naturally described in terms of field theory with these quasi-particle excitations, right? It was something specific to some systems. But we saw some key properties of field theory. Even in those examples, they were very obvious. They were showing quasi-particles, right? And then at finite temperature, we saw fluctuations, pair creation, right? We saw annihilation of these quasi-particles. And if you have energy, thermal fluctuations, you could pair create them, right? All those phenomena exist in quantum mechanics, quantum field theory, but you don't need temperature for it. These are quantum fluctuations. They're part of the description of the theory, intrinsically in there. Now, what I'm saying today is that quantum field theory is inevitable is simply because of the fact that quantum mechanics could not be reconciled with special relativity. We gave a couple of examples. Causality is often at stake. Causality is somehow violated. We saw some sort of superluminal propagation. We talked about the strong coupling problem. We talked about, what else did we talk about? We talked about something else. Oh, the fact that the particle number is not conserved because of the fact that if you want to localize a particle at a very, very small scale, you have large amount of energy. By relativity, that means that you can pair create, right? Any questions about what we've gone through? And then we talked about some advantages of quantum field theory. It explains spin statistics theorem, relating spin as an intrinsic property of particles to their statistics. And we talked about, what else did we talk about? Oh, this necessity of antiparticles. So at this point, I should tell you this, that what I'm advocating to you is that let go of the notion of particle. Particle is not a good, it was a good convenience as long as it lasted. But don't expect particle to be a fundamental description of nature. So fields are fundamental description of nature. At some point, a third throughout the course, I will have to say, okay, I said particles are emergent, but how do particles emerge out of field theory? How do particles sit inside the framework of field theory when the interactions are weak? I have to explain that, and we'll get there. And it comes out of relativity, again, as usual. A lot of things here, all the magic happens out of relativity. Quantum mechanics is difficult. Why? Simply because it doesn't have relativity. Quantum field theory is more constrained because of relativity. Relativity forces things on you. It requires some crazy consistency. All right? Okay, so what is quantum field theory? Good. It is a theoretical framework in development, meaning that there's no agreed upon definition of quantum field theory, that quantizes fields, functions of space-time as fundamental building blocks of nature, not particles, fields. The basic degrees of freedom in nature in this description are fields, functions, space-time. What are they? If you want to be a mathematician, they are operator valued functions of space-time. But what does that mean? It means that here's a function of space-time, phi I of x and t, and it's an operator. It's an operator valued function of space-time. Okay, so what are the observables of the theory? Can you observe the field phi? That's a question. The answer is that phi at the point in space-time is not an observable. Class, consider a field theory, field theory has equations of motion, the same way that particles had equations of motion. It's gonna look something like this. Oh, sorry, it's wrong. Correct, that's wrong. What I've written is wrong. For particles, what do you have? You have x double dot is equal to del x of the potential, v prime of the potential. That's F equal ma. Right? I'm just dropping m and all that. That's what it is. Here, you're gonna get minus F double dot. Here is the potential force term. But because this double dot came from the fact that in quantum mechanics, operators were function of only time. Here you have the functions of space as well, so you're going to get the second derivative in space as well, Laplacian. So the equation of motion for fields look like this. We're going to derive this from first principles, but it looks like this. So what is the solution of classical equations of motion in particle for the motion of particle describing? They're describing the motion of classical particle. Here, if you solve this, you find a function of space-time. You take the field operator and integrate it next to this guy, these solutions, and you've obtained phi of f solution. That is an observable of the field. Don't tell older colleagues of mine this slide. I might not agree with it, but that's old school. Their way of learning what an observable in quantum field theory is old school. This is what it is. Good. Is that clear what an observable is? So phi hat at the point xt is not an observable. You have to smooth it. You have to integrate it against something. Now, what are the principles of quantum field theory? Before we start constructing them, I'm going to tell you what the principles are, because as we construct them, you're going to see this over and over again. Locality, symmetry, positivity of energy. What is described by quantum field theory? With these three principles, we're going to describe this framework that describes fundamental theories of particle physics and cosmology, quantum gravity, some models of quantum gravity, many exotic low energy phases of matter and phase transitions, hydrodynamics, that's also field theory, and we're going to use field theory to construct, not us, but people do, to study topological invariance of manifolds. So it's a very, very useful framework. This is the end of this lecture. Now, where are we going to go with this? The first two lectures were just very high level talk, hopefully poking you guys the right way, looking forward to quantum field theory. By now, I'm hoping that you have realized that quantum field theory is not another, like set of equations or like some formulation that's good for something and it's just whatever. It describes a certain set of systems. Quantum field theory is a must if you believe in relativity, that you better do. And if you believe in quantum mechanics, that you better do, right? Because that's what describes our nature. It's a must, and it's an extremely general framework. The principles of it, I repeat, are locality, symmetry, and positivity of energy. So I'll stop to the slide. Are there any questions?
Anima, small question. Like in the last slide, I am not exactly sure what was your F solution. Like, is F itself a field or what is that?
It's a function.
Okay.
It's a
Okay.
function of space-time, right?
Okay.
I integrate the field, the operator value distribution, field operator, against this, and I obtain phi hat of F. That's an observable of the theory. You could measure it. Any other questions?
Okay, just for the clarification, so here F is the function of a particular point in space-time, and the field operator is also defined at that particular point, and then we are integrating, right?
No, when you solve the equations of motion, this is a PDE. The solution to this is a function of space-time. The solution to a PDE that has time derivatives and space derivatives is a function of space-time. Field is also defined at every point in space-time. So just put them next to each other, integrate against them, and you get an observable. Good. Any other questions?
Will the slides be uploaded to the website?
Yes. I'll try to do that tomorrow.
Field theory has have a Lagrangian or Hamiltonian formulation.
Yes, we're going to discuss this in detail. So let me give you a little bit of the outline. In lecture 3, you can see this already on the website, but next lecture is the beginning of this part 1 of the course, which was, is the end of the section 1 of the course, which was this: what is quantum field theory and why? Right? So all this high level talk is about what is quantum field theory and why. Then we're actually going to get our hands dirty and start doing stuff. But before doing that, the third part of this section 1 is next lecture, where we're going to go through the explicit example of a quantum field theory, very simple quantum field theory, that is a quantum theory of sound, otherwise known as phonons. So we're going to go through that. A lot of these phenomena that we're talking about, emergent low energy quasi-particles, all of that will come back. Phonons are quasi-particles. So we're going to discuss that as an example. And then that will wrap up the first chapter, I guess, of the course, which is just motivating what is quantum field theory and why are we talking about this, where are we spending this time discussing it. All right, any last questions?
Could you expand more on what you mean that QFT must have a principle of locality?
Yes.
I would think
We'll
that, yeah, I would think that quantum mechanics allows for non-local things. So, why are you requiring locality here?
Oh, no, I'll define what locality is. I think you're talking about entanglement and stuff.
Yes.
There's some unfortunate choice of words that cross disciplines, people use the same terms meaning two different things. So we'll define locality, we'll be very specific about it, and there's plenty of entanglement quantum field theory is perfectly fine. Here, by locality, we mean something else.
Okay,
We'll see.
thank you.
Yeah, well, we will have a couple of lectures on locality. All right, thank you so much. Oh, you had another question? Yes.
Just like for course stuff, like, will you post the homework on Brightspace?
Say it again, will I post what?
Homework.
Homework. I'll post the homework on my website.
Okay.
And I'll announce it in the class that I have posted it.
Okay.
Is that good?
Yeah.
Is that fair?
Yeah.
Okay. All right. Any last questions? If not, thank you so much, guys. Have a nice day. Bye.
Thank you.
Thank you. Bye.